times 17 factorial, right? So what happens to the two factorials on the top and the bottom? Well, since this is just multiplication and this is just multiplication across division, I can just cancel them out. Okay? And so what do I get? 18. So how many different ways can I choose one woman out of 18? Well, obviously just 18 times, right? That should be intuitive. In fact, we could probably guess that from looking at it without doing this, but again, prove the point. Now let's do the next one. Let's do 14p2. How many different ways can I choose two men out of 14 when order matters with no repeats? Well, that's permutations, right? So it's going to be 14 factorial over 14 minus 2 factorial, which is going to be 14 factorial over 16, or excuse me, 12 factorial. Well, I'm going to rewrite the numerator again. So this is going to be 14 times 13 times 12 factorial. And of course, that's going to cancel with the 12 factorial on the bottom. And so now I just get 14 times 13, right? Okay. Now, let me show you something. Remember the way we've been doing this with the license plates and with the identification numbers for the school, the students, and what was the other one? I think those two. But notice how when we were just writing out the dashes, look at these numbers up here, right? So what do we get on top here? We got 18 times 14 times 13. Right? Watch what happens. How many females do I get for the first position of president? 18. How many males do I have for vice president? 14. Now, how many men do I have for treasurer after I choose the vice president? One less. Use the fundamental accounting principle. Look at that. I get the exact same thing. So here's the thing. I don't have to memorize all these formulas if I just remember how to work it out by thinking about it. Okay? So because we've been using permutations without actually using the formula. But notice the formula works. Okay, so here's the proof. Okay? Now, what about the bottom number? Well, let's see. So we get 32p3. Well, that means that we have 32 factorial over what? 32 minus 3 factorial. And of course, that's going to give us 32 factorial over what? 29 factorial. Now I'm going to cancel the 29 again, right? So I'm going to rewrite the numerator as 32 times 31 times 30 times 29 factorial. And of course, that's going to cancel out with the factorial on the bottom. And I'm left with 32 times 31 times 30. Now, let's do our dashes like we have. So here are three spots, right? President, vice president, oops, not vice treasurer, vice president and treasurer. Well, if I take all the total possible outcomes, right? So genders, we're not interested in men and women, okay? So how many people do I get to choose from? 32. Well, if order matters and I'm not dealing with repeats, right? So how many people do I have to choose from for president? Well, 32. And then once I choose a president, how many people do I have to choose from for vice president? 31. And then finally, 30 for treasurer. Look at that. I get the same answer. So here's my suggestion. I don't use the formulas when it comes to permutations because I can just put out how many dashes I need and then just figure out how many I get after each choice. Okay? So I hope that makes sense. So now, let me see here. Now the question then becomes, what if order doesn't matter? Oh, hold on a second. We're not done with this. We're not done with this. Okay, so now we still got to figure out the probability, right? Hold on, let me get that. Oh, I love it. Okay, so now let me make sure we got this. Okay, so now here we go. So now the probability of getting these just turns out to be this, right? 32 times 31 times 30. And of course, if we reduce that, so let's do, so 18, 14, and 13. So 18, .110. So we get 0.110. That's the probability of randomly choosing a vice president, president, and treasurer where we get a woman as president and men for the other two positions. So that probability, if we randomly just selected 3 people, that we would get that as 0.110. Okay? Now, the other question too that they ask here, I wanted to make sure, where is it? Here. Now, it says, what is the probability that all 3 officers are female? Okay, so now, let's think about it this way. So the bottom number still stays the same, right? It's still the total number of possible ways, so that doesn't change. So let's look at this now. Okay, so we only have 3 spots, right? So, if I want all 3 to be women, well, how many women do I have to choose from? 18. How many spots are there? 3. So it's going to be 18p3. Now, how many spots do I have left over for men? 0. Okay, so that means how many men do I have? 14. How many of those men am I going to choose? 0. It's going to be, what? 14 choose 0, 14p0. Okay, now, how many different ways can I choose 0 people out of 14? Well, that's going to be 1. Okay, there's only one way to choose nobody. Okay, so, but if you want, just look at this. So 14 choose 0 is 14 factorial divided by 14 minus 0 factorial, which is just 14 factorial over 14 factorial, which is 1. Okay, any number divided by itself is 1, right? So now, it's always going to be that way. There's only one way. Okay, now, look at here. So you might ask yourself, well, why do we even include that if it's always 1? When you're choosing 0, it's always 1. Because I want to show you something here. Look at these 2 numbers. This is n, and this is k, right? These 2 numbers, okay? This n, right? So this n and this n should always add up to 32. 18 and 14 add up to 32. And then the 2 k's on top, this k and this k, should always add up to the k in the bottom. So 18 and 14 add up to 32, 3 and 0 add up to 3. That's why I included it. So that way when you guys first do this and you're starting out, you can always do a check to make sure you're not missing anything. Later on, when you get used to it, you can just ignore this and just realize you are doing it correctly. But this is a good check to do. And if you do look at the other example that we did for part A, you'll see that the numbers do match. Okay? So now, okay, let me make sure. Okay, so now, let's do this, right? So this is 1, right? So this is going to be, so 18, so that we know this is going to be 1, right? We just did that one. 18p3, right? That, using the formula, it's going to be 18 factorial over 18 minus 3 factorial. And so I get 18 factorial over what? 15 factorial. And again, I'm going to rewrite the bottom, right? So that's going to be 18 times 17 times 16 times 15 factorial. And of course, the 15 factorials are going to cancel. And I get 18, 17, and 16. Well, look up here. Well, if I want all women, right, how many women do I have to choose from? 18. And then once I have the president chosen, how many women do I have left over? 17. And then how many women do I have left over for the treasurer? 16. Look at that. Got the same answer. So now, what do we get on top? Well, all we're going to get is what? 18 times 17 times 16 times 1, right, if you want to include it, divided by what? The same thing we had before, 32 times 31 times 30. Okay? And if we do that, what's the probability we get? .165. So this is going to give us 0.165. Okay? I hope that all makes sense to you guys. Again, pause, rewind, watch it again if you have any questions until you understand what's going on here. Okay? So all I'm doing is I'm using permutations to find out what number goes on top and what number goes on the bottom. Okay? So now, what if order doesn't matter? Then I'm not dealing with permutations anymore. If I want to know an unordered arrangement, okay, so order doesn't matter, then now I'm not dealing with permutations anymore. I'm dealing with something called a combination. So I'm going to use this as an example just to show you something. So when we deal with permutations, order matters. So that means ABC is different than ACB, which is different than CBA, which is different than CAB, which is different than BAC, and different than BCA. And those are the only possible outcomes that we have. Okay? And by the way, how do I know that that's the only possible outcomes? Because I can use the fundamental counting principle, okay, in permutations. Well, if I'm choosing 3 letters, right, and I only have 3 letters to choose from, A, B, and C, well, I have 3 options for the first, 2 options for the second, and 1 option for the first. And if I use this fundamental counting principle, I get 6. So I have 6. So I know I have all of them. Okay, because I don't have any repeats. Okay, so now how many permutations are there here for these 3 letters? 6. Okay, now what if order didn't matter? What if all I cared about was having these 3 letters? I didn't care about what order I chose them in. All I cared about was at the end of my selection process, I look in the bag and yep, I got them. Okay, then we look at all of these different outcomes as exactly the same. So this would mean that this would be one combination. Okay? So whether I get BCA or whether I get ACB, it doesn't matter. I got all three of those letters. Okay? So that's the difference between order matters when order doesn't matter. Okay? So the difference in the formula is a slight difference, but it's important because your numbers will be different when you're dealing with probability. Okay? So a combination is written as NCK. Okay? And this is, we term this as N choose K. Okay? So how many different combinations of K objects can I get out of N objects if order doesn't matter? Well, the formula is very similar to the formula for permutations except for one addition. And it's going to be N factorial over K factorial times N minus K factorial. So the one piece that's different is this piece here. And the reason why that is because we're dividing out all of the distinct orders. So we're starting with getting rid of all of the distinct orders of size k. And then we're going to divide by k minus 1 to get rid of all of the distinct orders of that size. And then we're going to divide by k minus 2 to get rid of all of the distinct ordering of that size all the way down to objects of size 1. And so that's where the k factorial comes from. Okay? And that's really all you have to know is we're dividing out all of the distinct orders. Okay? Which means the number of combinations will always be much smaller than the number of permutations. So again, you've got to ask yourselves when you're looking at the problem, does order matter or doesn't it? Because if order matters, you're dealing with permutations. If order does not matter, then you're dealing with combinations. Okay? Just like if you're dealing with repeats or no repeats with permutations, right? Okay, so now, that's what we're going to be dealing with combinations. That's the formula. So now everything else is the same. The fundamental counting principle, finding the number that goes on top, finding the number that goes on the bottom when you're dealing with probability. It's just that now we're going to be dealing with a different formula for figuring out what number goes on top versus what number goes on the bottom. Okay, so let's take our example. So let's take, let's see. Now let's take our example that we had for the 14 men and 15 women. Now, let's say I just want to choose 3 people to go to a conference. Okay? So in this case, order doesn't matter, right? I just want 3 people to go to a conference. I don't care what order you chose them in. I just want 3 people to go to a conference. Okay? So how many different ways can I choose 3 people out of this club to go to a conference? Okay? Well, order doesn't matter, so it's going to be combinations. So how many different ways can I choose 3 people? Well, it's going to be out of how many people? Oops, that's 18. So how many people are there? 32. So out of the 32, I'm going to choose how many? 3. And since order doesn't matter, I'm talking about combinations, right? So that's going to be what? N factorial divided by k factorial divided by n minus k factorial. So what happens? N is 32, so it's 32 factorial, divided by k factorial, which is 3 factorial, and then divided by n minus k, which is 32 minus 3 quantity factorial. Well, now what does this reduce to? Now I'm going to start using my factorials, right? So this is going to be 32 factorial over 3 factorial times 29 factorial. So now I'm going to rewrite the numerator again, just like I did before. 32 times 31 times 30 times 29 factorial. And then I'm going to have 3 factorial in the bottom times 29 factorial in the bottom. Now, just like before, I can cancel the 29 factorials. And look what I have. I have 32 times 31 times 30 divided by 3 factorial, which is 6. Okay? So what I end up getting is 32 times 31 times 30 divided by 6. So how many possible ways can I choose 3 people out of the 32 to go to a conference? Well, it's just going to be 4,960. Much smaller than when we were dealing with permutations, because the total possible outcomes for permutations was 29,760. So much smaller when we're dealing with combinations. Okay? Now, that's using the formula. But think about what we did with permutations, right? What did we do with permutations? Well, to find the permutations, all we did was, well, we chose 3 people, right? How many people do we have to choose from for the first, right? We have 32. Then, how many people do we have for the second one? 31. And then 30. Well, the only difference is, remember, this piece that we're dividing by. So what I would do is just use the same technique and then just divide by k factorial. So just use the permutation and then just divide by k factorial. That's another option you can do. Okay? So in this case here, it would just be 6, right? So you can do that, but again, the formula always works. Okay? So now, what's the probability? So this is the total number of ways of choosing 3 people to go to a conference. Now, what is the probability that all 3 women, or all 3 people I choose would be women? Well, let's now use the idea of probability and use combinations. So, the probability that all 3 people would be all women, well, it's going to be what? The number of ways of choosing all women over the total number of ways of choosing 3 people to go to the conference, right? So on the bottom, I know it's going to be 32 choose 3. That's what we got here, right? Okay? Now, the top, I have men and women, right? So I have 3 positions. All of them are going to be women. So of the 18 women, I'm going to choose how many? 3. And then how many spots does that leave for men? 0. So the second number is just going to be out of the 14 men, I'm going to choose 0. Well, again, how many ways can I choose 0? It's going to be 1. So why do I do that? Again, make sure that the numbers add up. 18 plus 14 equals 32. 3 plus 0 equals 3. I'm good. So now, let's use the formula. 18 choose 3 is 18 factorial divided by 3 factorial times 18 minus 3 quantity factorial. Well, this is going to be 18 factorial over 3 factorial times what? 15 factorial. And so again, if I cancel things out, I'm going to get 18 times 17 times 16 times 15 factorial divided by 3 factorial and then divided by 15 factorial. And so the factorials cancel out again. And so look at that. I get 18 times 17 times 16 divided by 6. And so how many different ways can I choose all women? It's going to be 816. So this is going to be 816, which goes right up here. Oops. Is that 816? Yep, 816. So now I've got the numbers, right? So it's just going to be 816 divided by 4960. And so the probability is what? 0.165. And that's it. Okay? Now, what if I said, what's the probability of having at least 2 women on the committee? Well, I would have to consider what cases. I would have to have exactly 2 women or exactly 3 women. Okay? So now, how would I do that? I'd do the same thing and I would just use the addition rule, right? So if I want the probability of at least 2 women, that would mean I'd have to calculate the probability of exactly 2 women, right? Or all women, right? So plus the probability of all 3 women. Okay? Well, we did this one. This one was 816 over 4960. Well, let's see what the probability of this one is. Okay? Well, how many different ways can I get exactly 2 women? Well, let's look at this. How many spots do I have? Well, I have 3 spots, right? Okay? 2 of them are going to go to the women. So out of how many women? 18. I'm going to choose how many? 2. So 18 choose 2. That's going to be one group, right? Now, how many different ways can I choose 1 man? Well, how many men do I have? 14. So 14 choose 1. Now notice that 18 and 14, 32, and 2 and 1 make 3. So it adds up. And then of course the bottom is going to be the total number of possible outcomes, which again is going to be 32 choose 3. Okay? So this is going to be this probability, right? All I'm doing is applying the definition of probability using combinations to get my top number and my bottom number, and then just divide. Okay? So now, this is going to be 14. 18 choose 2. Well, let's think of that. Well, let's just do this, right? So this is going to be 18. I'm going to have 18 and then 17 and then just divide by 2. Okay? So times these 2 and divide by 2 is just going to give it to me. So pay attention. I'm not using the formula directly. I'm using what I talked about earlier, right? So I'm just using my dashes and filling in the numbers and then divided by k factorial, right? So the number of permutations divided by k factorial. So I didn't use the formula directly there. So it's going to be 18 times 17 divided by 2, and I get 153, right? So this number here is 153, okay? So 153 and 14, and then of course this is 4960, okay? So now, what do I get? Well, 153 times 14 is 2142. So now, what do I get? I get 2142 over 4960. So now I got this plus this. Well, so if I add both of these probabilities, again, I'm just going to leave them as fractions because it's easier just to add the numerators. So what do I get? I get, let's see, let's add the 816 And I get 2958 over 4960. And what's that probability? .596. So that's the probability that if I randomly selected 3 people to go to this conference, that exactly 2 of them would be women. Or excuse me, that at least 2 of them would be women. So that would be 0.596. Okay? Okay, so now, let's see. So one last thing about combinations. Okay? And I'm going to close with this because I think that's all I want to cover. Okay? These are actually properties of combinations. So the last thing that I want to talk about, and it's the fact that well, we often call combinations binomial coefficients. I'm not going to get into that right now, but they're called binomial coefficients because they're symmetric, just like if you do a binomial expansion. Okay? But realize that one of the properties of combinations is if you have n choose k, that's going to be always equal to n choose n minus k. So in other words, if I am looking for 10 choose 3, that it will always be equal to 10 choose 7. Okay? That's a property of combinations. This will always be the case, and it's because these also follow a binomial type of distribution, the binomial formula. Okay, but anyway, that's all we need to know for that one. But just realize that's the other property, and so this ends chapter 3 on probability. Okay, so everything you need to know to solve any problems with probability, we've gone over. Okay, so again, make sure you go over these examples yourself. Make sure you review this over and over again, pause, take notes, and then just make sure you understand when you're attaching it, because if you understand these, it's all about understanding the problem. So read the problem very carefully, and then figure out what you're dealing with. Are you dealing with permutations? Are you dealing with combinations? And then you just apply the probability rules that we talked about and the definition of probability. That's it. Thank you, and I'll see you next time.